Good afternoon and welcome to today's session of Introducing Air Tightness. My name is Jessica Allen. I work for SUHO. I'm in the Adelaide office. And let's get started. We've got about half an hour of fun facts to get through. CPD points are available. Email us at info@suho.com.au. All of our webinars are pre-approved for a Green Star Sustainable Development point. Flick us an email and I can send you a certificate of attendance. Just interact in the chat so that we know that you're there. Okay, so I will make time at the end for some questions, so please feel free if you have any questions to put them in the chat, and I'll get to them at the end. It's a bit hard to look between this screen and that screen while I'm talking, so I'll just power through and then we'll have time for a bit of Q&A at the end of the session. So today we're going to go through some basics. What's blower door testing? What happens on site during a test? Why would you have improved air tightness? Some information on how air tightness can help bushfire resilience. We're going to touch on the building code changes that are now in place as of last Friday, and we're going to touch on Green Star testing as well. So what is blower door testing? Blower door testing is a way of putting a number on the amount of air moving through the building fabric that shouldn't be. So it shouldn't be confused with ventilation. Windows and doors and ventilation systems are not taken into account in this number that we're trying to work out. What we're trying to work out is what is the integrity of the building fabric, what's the air barrier like, how effective is it, and we want to quantify exactly how much air is leaking out of a building into the atmosphere that's wasting energy. Because you condition a building, whether it's a house or a large office building or a hospital or whatever it is, you condition it and you don't want that expensive conditioned air leaking out of the walls and the roof. So this is a way of putting a number on that on that leakage factor. The Your Home website states that between 15 and 25% of winter heat loss occurs via leakage. So that's a lot of money just leaking out of your walls and your floor and your roof. So the key word in this definition here is uncontrolled. Air leakage is the uncontrolled movement of air through unintentional gaps and cracks in the building fabric. So we want to start controlling where the air goes. If you're pumping conditioned air into your building, you want to control it. You want to keep it in there for as long as possible. You must also at the same time, depending on how airtight your building is, ventilate it. You can't create a really airtight structure below a certain level without also adding in deliberate mechanical ventilation. So there's a very delicate balancing act there depending on how airtight you go. But the beauty about an air tightness test is you get a number to work with. So during a test, we will bring equipment to site. Prior to coming onto site, I'll work out the size of your building, the square meterage of the building envelope, and that will help me to work out how much equipment I need. In a typical house, we won't need any more than one fan. In office buildings and larger buildings, we often require many, many fans. So the biggest test I've done has been 8. Typically between 3 and 6 fans is required for most of the office building tests that I've done. The fans are installed in a temporary frame that gets installed into external doorways in the building. The fans are then all hooked up with tons and tons of wires and hoses to make sure that the information is being read from the right place and delivered to the right place. And then we turn the fans on and we exert negative or positive pressure on the building. The equipment that we bring along measures how much air is required to pressurize that building to 50 pascals, whether that's negative or positive. And then the readings are all pumped through to the computer. So the top graph that you can see is the readings that are taken from a test with more than one fan. You have to use different software if you're using multiple fans than if you are using only one. So the bottom graph is a one fan test, and all those red dots are readings. The readings are taken at different intervals, up to 65 or 70 pascals and down to about a minimum of 10 pascals. So all of the readings are taken at various intervals and then the results are worked out based on those intervals. The results are always represented at 50 pascals though. So finding leaks is the fun part. There are a few ways that we can do that. and we look around these areas in this picture. This is a typical older house, lightweight cladding, could be block work or double brick. Just for argument's sake, this picture was taken off the Your Home website, which is a very useful resource. And this house has got a timber floor, it's got a chimney, it's got a air conditioning system in the wall, it's got a vented skylight. This house is a typical example of where you might find a lot of leaks in a typical older home. It's got air vents in the walls that have been designed into those older types of homes. And then other things like electrical and plumbing penetrations, downlights, exhaust fans, taps, anywhere where there's a hole being put in the fabric of the building. The floors in these really old homes are a big leakage point as well. Just as a fun fact, I don't come across many of them, but the ones I have come across, the floor is a big factor. I actually have a friend who says that she gets dust on her floor that comes up between the floorboards. So I'm sure she's not the only one. So to find the leaks, the most common way is just by feeling with our hand. And that can be quite a fun exercise to go through with the client, just going around and pointing out stuff to them that they wouldn't have otherwise thought of. So that's this little thing here. We go around all of these junctions, doors, downlights, windows, any penetration, we go around and feel for leaks. The other way is using smoke. So this puts a bit of a visual on it. This is an example of a PowerPoint leak. So it's quite common for PowerPoints to leak. There are specific fittings you can get for the back of PowerPoints that make them airtight, but for the most part, penetration goes into the wall, and then the air pathway goes up to the roof space. So PowerPoints, although you wouldn't normally think of it, and when you put 15 of them in a house, they are leaking air all day long, unless you have those little kiddie safe plugs that you put in them. And then thermal imaging is another really cool way of identifying leaks. So this picture here, you can see the purple splashes around that fitting there. The purple splash marks are air leakage. Oops, next slide. Here's some more thermal images of some air leakage. This one here is an air conditioning vent leaking quite a lot. This one was a really fascinating job. This was supposed to be a 7.5-star home that was built north of Adelaide about 10 years ago. We actually did the energy assessment at SUHO. And when I went to visit this home, the clients were complaining about being extremely cold in winter, and I took a tradesman with me on the day, and we tested the house and identified tons of air leakage pathways that we were able to fix up quite quickly. But all of the windows in this house leaked like this behind the architraves, every single one. So this was a really good example of where leaks were happening all through the house, all through the downlights. They'd cut a huge hole behind the fridge, about yay big, to ventilate the fridge, that went directly out into the shed. So things like this, they just hadn't thought about the knock-on effect of what they were doing. They had a reason for what they did, but affected the comfort of their house in the meantime, and then the construction quality just wasn't there. So the 7.5 stars in practice wouldn't have been anywhere near it, because the house wasn't built in accordance with how it was supposed to be built. This one here is a picture of a missing insulation bat. This is another really, really common defect that we find in new houses, where the electricians have disturbed the insulation to do their work and then not replaced the bats. Something like this is invisible unless you actually get up into the roof, which most people don't do, or you have a thermal imaging camera and someone who knows what to look for. So this is another really fascinating thing that clients are always surprised to find out about. We have had some builder clients actually go out and buy thermal cameras for all their site supervisors to make sure that so they can actually audit their own buildings, which is a really good idea. The bottom image is a steel framed home. So as you can see, the frames on a steel frame home light up big time. There's a lot of thermal bridging going on there, bringing outdoor temperature straight indoors. So these two bottom images aren't much to do with air leakage, but they still impact the comfort of the home, and they are part of what we look for in an audit process. The red pen test is something that if you've identified that you need an air tightness strategy for your build, then you will need a red pen test. I mean, it's called a test. It's not actually a test. It's just a drawing. So you grab a red pen, or it could be blue if you want. It's just red for the purposes of demonstration, and you draw a line around your air barrier. This line generally follows the insulation. It's a thermal barrier as well as an air barrier, generally speaking. So it's going to separate unconditioned zones from conditioned zones, typically car parks, with parking areas, plant rooms in commercial buildings, things like that. As you can see in the image on the right, the left, sorry, on the right, the garage has been excluded from the red pen test in a residential building. And the reason for that is that it's cold out there in winter, it's hot out there in summer, there's all sorts of chemicals and dust and things in a garage that you don't want entering your home. So you're going to draw a line around that and identify to the trades on site that this barrier between the house and the garage needs to be complete and needs to be airtight, so that the fumes don't come in, the heat and cold doesn't come in, and the integrity is maintained. There is a specification that some of us at AVA wrote about a year ago. Let me see if I can find it, because I've said I'm going to put it in the chat, so I'd better do that. I'll just find it and I'll put it in the chat for you, because it's a really useful document that you can add to your plan set to let just makes it easy for you to set out exactly what's going to happen. It demonstrates an intention to get an air tightness test done. It identifies what the targets are and how the test is to be carried out. So I'm just going to, here we go. Oh, come on. AVA. Test guide specification. Here we go. Here we go. Copy, paste. Here we go. Right. That AVA link there will take you to a specification that was written by myself and some colleagues about a year ago. Have a look at it. If you've got any questions, please let me know. But it's there for you to use. It's a free resource. So the air tightness tests the results are represented based on the size of the building and the amount of air that's required to pressurize that building. So as I said earlier, we work out the envelope areas before we come to site. The dark green area indicates what the envelope area typically is. It's the external surfaces of a building, and that's measured in square meters. The light green in this picture demonstrates volume of the building. So the equipment will work out exactly how much air is required to fill that space and pressurize that space to 50 pascals. Then, 4 pascals. Yeah, so that would be the envelope area. There's a few different types of tests that we can do. The whole building test on the left here is the best way to carry out a blower door test. It's the best way to get the most accurate number. These other types of tests here, smaller compartment tests, and this one is called a guided blower door test or a co-pressurization test. Very similar to a compartment test where you're only testing a small portion of the building, but you're actually co-pressurizing the surrounding zones to cancel out any internal leakage. So this test here, the numbers that you're going to get out of this test are not going to be accurate at all or useful, because it's going to be quantifying a lot of internal leakage, which is not what we care about when we're doing a blower door test. We want to know what's leaking out into the atmosphere, not what's leaking out into the next room, because that's all within the building envelope. These tests here, these co-pressurization or guarded tests, you can see these red zones here are the guard zones and the green zone is the test zone. So the red zones neutralize the internal air leakage to a certain degree. They need to be very carefully prepared, and there's a lot of internal mechanical risers, there's ducting, there's vents, there's lift shafts, there's all sorts of things that are going to be interfering with the air pathways in a complex office building that all have to be excluded from the test, which means a great deal of time needs to be spent in preparing the building using temporary sealing measures. So and the same thing with a compartment test. So these two tests, although they might seem like they're more straightforward because they're a smaller test, it's actually much more straightforward to do a whole building test and just close off all the mechanical systems, force shut all the dampers, and off you go. It can be as simple as that depending on the building. And I go through all of that a little bit more in more depth in the Green Star discussion, the Green Star webinar that I've done. So if you want to know a little bit more about the different types of tests, you can go through our library on YouTube and go back and find the Green Star topic that I covered. And I'll probably touch on it again in a couple of weeks if anyone is interested in knowing more about how these tests are carried out. The benefits of an improved air tightness strategy is obviously reduced energy costs because you're not having your expensive conditioned air leaking in and out of the building willy-nilly. You're more comfortable because obviously the air stays at a more constant temperature. You've got a healthier indoor air quality because you're not having any pollutants from outside entering your building when they shouldn't be. So you've got reduced small particle infiltration, less risk of allergy sufferers will be more comfortable. There's also the risk, of course, of over-tightening a building and having the flip effect of having unhealthy air inside because it's not ventilated correctly. So we're back a few slides when I talked about air tightness strategies, depending on what the level is, also requiring a ventilation strategy. The number will tell you exactly where your building is at and what kind of ventilation it needs. If you go very low, below about 2 or 3 air changes per hour on your air tightness test, then you require mechanical ventilation or an extremely active passive ventilation strategy. And most of us aren't all that great at opening and shutting windows. It's important to understand exactly what you're doing and the impact you're having when you have an air tightness strategy, and which is why the test is really useful because you get a number. That information, that data is very important. Optimal mechanical HRV performance. So if you have a heat recovery ventilation system, if you have a leaky building fabric, then the internal temperature, the air temperature inside the building isn't going to be as stable as it should be. And that means that there's not as much heat to recover. So when the outside air and the inside air cross paths, there's not as much heat transfer going on because the indoor heat is leaking out of the building. So in order to have an efficient HRV system, you need to have an airtight structure. And our little friends down the bottom, these pictures, I think people probably look at these pictures and stop listening to me when I put this slide up. But I've got spiders, roaches and mice in my house because my house is a 1980s brick veneer beauty. And these guys come in through all the gaps and cracks that shouldn't be there. So if you don't like spiders or cockies or mice, then an air tightness strategy is for you. Bushfire resilience. So I'm sure, although we're all in the thick of this corona fiasco, I'm sure we can all remember back to December and January when the fires were ravaging our country. I had a friend in Canberra who posted this on Facebook. She said, after a brief respite, the smoke is on its way back. Time to take the doors and windows again. So although they weren't in the middle of the fire front, they were being heavily impacted by smoke. And in order to prevent the smoke coming inside their house, they had to tape the doors and windows. And I'm sure they weren't the only family in Canberra or all the way up the East Coast that had to do this. So an air tightness strategy is going to protect you and your family from smoke ingress. Jonathan Milford, this is an example of an article I found in the Canberra Times that just said his house was a little bit less smoky inside than out, but not too much less smoky. So a very similar experience to my friend. My friend had a small baby at the time, so this was quite a scary time for her. Air tightness also helps resist ember attack. So if you ever see, footage of a fire front where there's like a helicopter or a drone or something that's taking footage from up high, you can see there's maybe a fire front that's come across and then there's spot fires. Or you might just see footage of spot fire where one house is burnt down in the middle of a paddock and everything else around it has not been touched. I know I've seen that a few times. Those fires were caused by ember attack. Now, air tightness will not only prevent smoke from getting into your house, it will prevent embers from getting into your house. Because what happens is the embers settle inside window frames and then, or any other nooks and crannies where they can kind of get comfy, and they smolder. And behind windows, there are usually curtains which catch a light. So this is how fires can very easily start. So these embers can travel up to 40 kilometres. So spot fires can occur well ahead of the fire front. So just because you're not in the flame zone or any of these other, bushfire attack level zones doesn't mean that you are not going to be affected. The lower bell zones are actually based on the likelihood of ember attack. So embers typically get in, or they are opportunities are there for smouldering and ignition in gutters, underneath doorways, through cracks around window frames, gaps in roof spaces, and under floors, so under timber floors if there's debris under the floor. So obviously there's the risk of leaf litter on the ground, the fuel load on the ground, that is going to increase your risk. But if you've got an air tightness, if your building has had an air tightness strategy or had a blower door test and you've addressed some of the air tightness issues, it's not going to stop your house burning down if you're really in the way of the fire front or if the fuel load catches on fire. But if you have a little sneaky little ember or a few embers, it might will reduce your chances of those embers settling in and catching on and igniting the rest of the materials around it. The AS3959, which is a construction in a bushfire zone Australian standard, addresses combustibility of materials, and it addresses distances from vegetation and things like that, but it doesn't address air tightness. So I'm hoping that the next revision of this standard might possibly include a blower door test, because that would be a very sensible new strategy, in my opinion. This graph on the right-hand side is taken directly from a CSIRO study that was done 5 years ago now. It's hard to believe it was 5 years ago, but they studied 130 houses across the country. New houses, the houses were no more than 4 years old, and they tested their air tightness. So they did a cross-section of all the states and territories, and we've got data from Adelaide, Brisbane, Canberra, Hobart, Melbourne, Perth and Sydney. As you can see, Melbourne, Perth and Sydney had a much higher average than the rest of the country. They had a few pretty crazy outliers. I don't know how you achieve 37 air changes per hour in a house that's only less than 4 years old. I don't know, unless it was deliberately designed that way with louvers and things like that. I can't imagine that being the case in Melbourne, being a climate zone 6 city. So the results, some of those outlying results are quite alarming. In South Australia here, we did pretty well. So that's good news, but across the country, the average air tightness was 15.4 air changes per hour, measured at 50 pascals. So 50 pascals means that inside the house was 50 pascals different to outside, air pressure-wise. To put that in context, the gold standard of residential design globally is Passive House, and their air tightness target is 0.6 air changes per hour at 50 pascals. So there's a big difference between where Australia is currently scoring on average and the Passive House standard. And that's not to say we should all be trying to reach for the Passive House standard. There are a lot of people who are. You don't have to. There is a very safe and sensible middle ground there. Speaking of which, let's get to the building code. So Volume 1 is the commercial building code, and they've got some different requirements for different class types in different climate zones. So it's all a bit wordy and a bit confusing, and it's not really all that consistent, but the figures are there for you to read. Basically, they are aiming for 10 cubic metres per hour per square metre or 5 cubic metres per hour per square metre, depending on climate zone and building type, building class. The residential version is much more straightforward. They just put in a score of 10. You have to get less than 10. This is an optional test at the moment. It's a performance solution for the building ceiling section. So you don't need to do this test, but you can if you want to. And someone like me would recommend it purely because it puts a number on something that's invisible. And I don't know, I guess I just like to know. I'm a bit nosy and curious like that. So I've tested my house and it gets about 12. And I'm getting mice and stuff. So give you an indication. Because the mice aren't coming through open windows or doors. They're coming in under the, I don't know where they're coming in, cheeky little buckets. So you may have noticed that I've been talking about air changes per hour on this slide, and now I've switched to cubic meters per hour per square meter. So there's two different ways to talk about air tightness, and one is air changes, one is cubic meters per hour per square meter. In a residential application, they're pretty much the same thing. So we won't worry too much about that. Talking about the difference between the two. Excuse me, I just got a little visitor here. I'll be out there in a minute. The air changes per hour and the cubic meters per hour per square meter are both talked about quite commonly. Air changes is mostly used under a residential application. Passive house uses it. The cubic meters per hour per square meter is used more commonly under a commercial setting. And there is a reason for that, but I won't go into it now. The Green Building Council of Australia is one of the few organisations that requires an air tightness test under their commissioning credit, their building commissioning credit. So in order to achieve a Green Star point, you must employ a suitably qualified practitioner, and a suitably qualified that's a tongue twister. Suitably qualified practitioner is someone who is found on this website. So this is the ATMA website, the Air Tightness Testing and Measurement Association. They're a UK-based organisation, and we now have an Australian and New Zealand branch of that. They are the people who list all of the testers in Australia, the ones that are qualified to do these tests. There are about 50 of us in Australia, and in order to qualify for the points, you have to get one of these people. You can't just get any old person, not that anyone who isn't registered will probably have a fan, because the equipment's expensive, and if you can't get the work because you're not on the ATMA register, then that obviously doesn't make sense. So you have to make sure that you've got someone off of this list to do the test for you. You also have to make sure the person who you choose off of that list has got the experience and the equipment to actually carry out the test. There is a very broad range of skills and experience on this list. So just do your due diligence whenever you're picking your contractor and make sure that they know how to effectively and properly carry out a complex big building test. There are different levels, so you can get 3 points under this credit. 1 point if you achieve the minimum requirement, which is a very low bar, by the way. Achieving 20 cubic meters per hour per square meter is not difficult, and I would say that most buildings, not all, because I'm sure there will be some out there that won't pass, but most buildings will achieve that score. So if you're afraid of getting an air tightness test done because you're not sure what it all means and if you'll pass, my comment on that is don't be scared. Just get someone in on the project early enough that you can actually address the issues that need to be addressed throughout the build process. There are also innovation points available in air tightness. So you can have 1 additional point for achieving the next level up, and then you can get 2 additional Green Star innovation points for achieving best practice. There's a little bit of jargon in here about what areas of the building you have to test. Unfortunately, this wording here allows this test here to happen. This compartment test, which, as I mentioned to you, the numbers that you get out of that test make absolutely no sense. So it's quite problematic, and we have colleagues in the industry have been kind of chatting with Green Star to try and nut that out a bit and try and make it a little more, make a little bit more sense, because the perception is that that kind of testing is the cheapest, easiest way to test, and people just want 1 point, and it's a bit of a waste of time. Again, if you want to know more about Green Star testing, you can go back in our library and find one of the webinars about Green Star testing, or I'll be revisiting it again in a week or so. So having a little bit of a think about where Australia sits in comparison to the rest of the world, our average is 15.4 air changes per hour. I've got some switching out in jargon here, but that's just the nature of the beast, unfortunately. The UK is their code minimum is 10 cubic meters per hour per square meter, and they actually have to do 2 tests. I think they have to do 2 tests, one halfway through the build to test the air barrier, and then one at the end. And it's the case over there where sometimes you can't get occupancy without a compliant blower door test. And the guy from ATMA tells funny stories about how there's trucks in the driveway waiting to move people into their new house, but the blower door contractor says, sorry, this test failed, and the people can't move in. So we're not quite there in Australia yet. We've got a long way to go before we've got some mandatory testing in place. The option in the building code, as I mentioned, is optional. But we're on the right track because it's now at least in the building code and people are talking about it, and people such as yourself are learning about it. So that's good news. Passive house has to get 0.6 air changes. Department of Defence have got very similar guidelines to the Green Star. So these little figures here are more or less aligned. They get their benchmarks out of the ATMA standards. Next week's schedule, I went to find it to let you know what was happening next week. It's not quite released yet, but it'll be out later today on our social media networks. So stay tuned for that. There'll be some new content next week. And that's all I have today. So thank you very much for your time, everybody. And Green Star CPD points, contact me at info. And anything else, contact me at the Air email address. I'll be happy to chat. So let's head over to the chat. Let's see. Vinny, would you normally seal off chimneys in a test? Yes and no. So I would seal a test, do one test without the chimney sealed, and then seal it up to show the client the difference. And those things, whew, man, do they leak. My parents have got one in their place, and they've put this piece of like strong, like not ply, like this, I don't know, strong cardboard or something up against the chimney, and then they've propped another heater up in front of it to try and stop the air leaks. But I blower door tested their place as well, and the piece of whatever it is that they've got in front of the chimney just went straight out and hit the back of the heater they had propped up in front of it. So it wasn't secure to the chimney at all, which meant that they were still getting air leaks, and their house is freezing. It is absolutely freezing in winter. So I was like, I gave them a few things, do this and do that, and they were like, oh, wow, that's awesome, never thought of that. It's fun. Another question from Vince. Do you know if there's any updated information relating to this data? Are we starting to build more airtight homes? The ATMA lodgement system, so the Air Tightness Testing and Measurement Association, every test that's done in Australia by an ATMA tester has to be uploaded to the lodgement system. So I don't have any current data to give you off the top of my head, but the data is being collected every day across the country as to what the results of the different tests are. So I can, maybe Barry Cope is the gentleman who I would speak to about getting those results. He might be able to pull some data out of the database for me and let me know. That would be an interesting question to ask him, actually. No worries. That's it. So thank you for joining me, anyone out there watching live, anyone out there who's watching on replay. I hope you also learned something today, and we'll see you next week for some more webinars. Have a good weekend. Bye.